Today we're going to learn some postulates and theorems to help us prove that triangles are similar. So once again, we're no longer going to have to prove that all the corresponding angles are congruent and all the corresponding sides are proportional. These theorems and postulates give us some shortcuts. So the first one is the angle-angle similarity postulate. I didn't mean to write that. I want to call it AA. Probably not the AA you're thinking of, but the AA similarity postulate. And it goes like this. If two angles of one triangle are congruent to two angles of another triangle, then I know that those two triangles are similar. So, in other words, if angle K is congruent to angle Y and angle J is congruent to angle S, then I know that triangle JKL is similar to triangle XYZ. From time to time, I may slip up and say congruent instead of similar, so please forgive me if I do that. Know that this unit is on similarity, and I do wish that you would let me know in class if I have done that anywhere in my recordings. Okay, we also have a side, side, side. Just like we have a congruence theorem, we have a side, side, side similarity theorem. And it says if the lengths of the corresponding sides of two triangles are proportional, not congruent, then the triangles are similar. So in this case, if I know that all the sets of corresponding sides are proportional, then I can say that triangle ABC is similar to triangle PQR. So I don't have to prove anything about angle congruence. If I know all of the corresponding sides are proportional, I can hop right in there thanks to this theorem and say those triangles are similar. All right, we also have a side-angle side similarity theorem. And it says if an angle of one triangle is congruent to an angle of a second triangle, and the lengths of the sides including these angles are proportional, then the triangles are similar. So we've got X congruent to M, and if XZ over MP equals YX over NM, then we can say that triangle XYZ is similar to triangle MNP. Okay, so those are our similarity theorems, postulates. So let's go. How are we going to use that? Is triangle ABH similar to KLH? Well, look, here are the ways we're going to prove that triangles are similar. It's either going to be by angle-angle, side-side-side, or side-angle-side. So we got three options here. I'm thinking there's no sides. I don't know anything about sides, but hey, look at this. I've already got the right angles, so I'm going to say yes. They are similar. By angle-angle similarity. And how do I know that? Number one, the right angles. We're not doing this as a proof, so it doesn't have to be as formal. So I know the right angles are congruent. I know the vertical angles are congruent. Therefore, by angle-angle, I can say that those two triangles are similar. Okay, let's do some more. Which of the following triangles are similar? Okay, well, it's clear to me that I'm going to have to show that corresponding sides are proportional. I'm going to have to use side, side, side here because I don't know anything about angle congruence. So I'm just going to take off and do that. I'm going to call this triangle A, and I'm going to call this one B, and I'm going to call that one C. And so let's check and see if A and B are similar. So let's check A and B. What am I going to do? I'm just going to put my corresponding sides. And here's one, like I told you about in an earlier lesson, where I don't necessarily know just by looking which angles correspond. So I'm going to pick the short side and divide it by the short side. So that'll be 12 divided by 15 in B. Does that equal medium side, 16 divided by 15. And does that equal, oh no, not 15. 15 is the shorter side. Sorry about that. 15 is the shortest side in triangle B. I got to pick the medium side, which is 20. And then the longest side in triangle A is 20. And the longest side in triangle B is 25. So is that true? I mean, are they all equal? So let's see, 3, so that's going to be 4/5. 4, that's going to be 4/5. And 5, that's going to be 4/5. So yes, so A is similar to B. And now I got to check B and C and A and C. So I'm going to pause here, let you check the other two, and then you can check your work. Alrighty, so when I write the ratios of the corresponding sides for triangles B and C, right away I can see that the corresponding sides are not proportional because I can't simplify this, I can't simplify this one, so no, I know those triangles are not similar. When I put down my ratios for the corresponding sides for A and C, I do get 3 fractions that I can simplify, but when I simplify them, I see that they're all different, 6/7, 8/9, 10/11. So no, these are not similar either. Only triangles A and B are similar. All right, let's look at these two triangles. Is triangle DFR, I'm going to highlight that, DFR, that's the big one, DFR, is it similar to MNR, this little guy right here? All right, well, you know what's interesting? I have the side lengths, and my first inclination was to set up corresponding side lengths ratios. But if you look here, I have this angle, and don't they both share this angle R? So yes, these two are similar by angle, and I don't even have to worry about the ratios because of my friend, the angle, similarity postulate. Couldn't remember if it was a postulate or theorem. Okay, so you still would have found them to be similar if you had done the ratios of sides, but hey, take the easy way when you got it. Okay, let's think about this one. How are we going to prove that triangle RSV is similar to triangle, so RSV similar to YXV? Well, it looks like side angle side to me because they've given me two sets of sides, corresponding sides. I know that these angles are congruent. So let's just make sure that we do have proportional corresponding sides. So let's take RS, no, not RS. How about SV? Let's list our corresponding sides ratios. So SV should be to XV as VR is to VY. So let's see if those two ratios are the same, and then we do know that we have similar triangles. SV is 20, XV is 24, and the question is, does that equal VR 15 over 18? So 4 goes into 25, goes into that 6, 3 goes into 15, 5, it goes into that 6. So yes, they are similar by side, angle, side, similarity theorem. Postulate. Which one? You check. Okay, side, angle, side. All right. Oh boy, real life problem. To comply with ADA, wheelchair ramps have to have a height to length ratio of 1 to 12. At a new construction, the height to the bottom of the door is 2.5 feet. So this right here, 2.5 feet. height to the bottom of the door. All right. Use the proportion A over B equals H over R to estimate the length of the ramp. Okay, so 1 foot, A equals 1 foot. So let's just plug in what we got. 1 foot to 12 feet. I know that H is 2.5 feet. I don't want to put a decimal in there. You know I don't like decimals. 2.5 as a fraction is 5/2. We're going to put 5/2 in there because we don't want to use our calculators. And I'm trying to find R. So R is my only unknown. So this is good. I don't need to switch anything or simplify anything. I'm just going to go right on and take my cross product. R is going to be 12 times 5/2. And when I do that, 2 goes into that 6 times. So R is going to have to be 30 feet. 30 feet. That's all I got to do right there. Set up my proportion, take the cross product. Okay, here's another one. I would very much like for you to pause here, draw this figure, set up your proportion, and figure out how tall the Washington Monument is. Alrighty, so here's how I drew my figure. You see I got my little person down here, my little person who's 5.5 feet tall. That's not too short. Okay, and he's casting a 4-foot shadow. Now anybody who knows anything about the sun knows that I have drawn my shadows incorrectly because the sun is making both of these shadows, so naturally both shadows would be on the same side of the figure. So let's pretend like the guy's not beside the Washington Monument. They're at different places, but at this particular time of day, his shadow's 4 feet. The Washington Monument casts a shadow that's 400 feet. And so what we got to do is set up a proportion to help us figure out how tall the Washington Monument is. So what I did is I took the height of the guy and I divided it by his shadow length. And then I said, okay, that equals the height of the Washington Monument divided by its shadow length. In looking back, I wish I had done it different, but oh, it's okay because of one of the properties I can switch. I'm going to switch my means here. Remember how we like to do that? So I'm going to have 11/2 is to x as 4 is to 400. And why do I like that? Because I can simplify 4/400ths, and that's going to give me 1 over 100. So then when I do my cross product, I'm going to get x equals 100 times 11/2. I'm going to simplify. That's going to be 50. So let's see, 50 times 10 is 500 plus 50, so that's going to be 550. I believe that's correct. 550 feet. And if I'm not mistaken, you can check me, Google it, but I do believe the Washington Monument is right around 555 feet and a few inches tall. But anyway, you can see the value of understanding similarity and proportions in finding out things. So, all right, write yourself a summary there. And our next lesson, we will talk about similarity in right triangles.